Okay, so it is 25 years since the top quark entered our consciousness, and we have spent that time studying it in some detail. And so it is appropriate, I think, that we stop and understand what the top has been able to teach us and a sense where we might be going in future studies. Just one little word on the prehistory to the top quark. Back in 1975, when the tau lepton and by inference the tau neutrino were discovered, followed by the discovery of the B quark a year later, and understanding that it was a member of an isodoublet, it didn't take very much genius to understand that there was something missing in the periodic table of the quarks. And since the mass of the B quark was about 3 times that of the charm quark, which in turn was... Same?
I think the question is whether you will show our slides or not.
Well, I was showing the slides, I thought. Let me try again.
No, please try again.
Do you see?
No.
No.
You should push on the green button demonstration screen
Yes,
and
yes.
find out.
Yes, I've done that.
And find out what file you would like to make visible.
Yeah. All that is done.
But we can see only you. We do not see your
If
presentation.
you like, I can share your slides.
Fine, that would be fine, Peter.
Oh, yes, now we can see.
Okay, thank you. And if you would, go to the second slide, please. I'll tell you when to switch. Next slide. Back. That's all the way at the end. We need to go back to the beginning. There, thank you. Okay, can people see now?
Yes.
Yeah. So quark prehistory.
So, as I say, we need not have much genius to understand that there's something missing. And so there were limits that were set successively at the electron-positron colliders, Petra, Tristan, and then LEP, that went above this mass of 30 GeV for the TT bar bound state. Did not see it. There was a sighting, or at least a reported sighting at UA1 at the CERN SPP bar S, looking at at evidence for the top decay to a B and a virtual W. But this was later retracted due to an underestimate of the W plus jets background. And subsequent to that, the UA2 experiment ruled out top anywhere below the W boson, looking for the W decay to a top and a bottom. And then passing to the Tevatron, CDF, and then the D0 experiments search for the top quark pairs in the case where the top decays to a W and a B. And ultimately, D0 raised the limit to 131 GeV. And the Tevatron was the only place to seek the top. So next slide, please. 2 Tevatron detectors on the left, the CDF, and on the right, the D0. CDF started in 1987, D0 only in 1992. They were complementary in their initial configuration. CDF had a solenoidal magnet surrounding a tracking and importantly, a silicon vertex detector used for tagging B quarks. And the D0, no solenoid, but a hermetic, finely segmented uranium liquid argon calorimeter and extensive muon coverage. So in 1992, the 2 experiments began what is now known as Run 1. Next slide. The top mass window. We know a lot from precision measurements, largely at electron-positron machines, on the constraints for heavy particles. Virtual top and Higgs loops in both the Z and the W boson propagators modify the properties in a way that depends on the top mass. And so measurements of those properties can give you a window on where the top and indeed the Higgs boson can exist. So by 1993, those precision measurements from LEP and SLC together with that top mass limit from D0, constrained the mass of the top to somewhere in the range of 155 to 185 GeV. It also set rather weak constraints on the mass of the Higgs boson. Next slide, please. The top decays 100% of the time to WB in the standard model. The W's can decay to a lepton and a neutrino, or to a quark antiquark. So the final states that can be reached from top pair production are completely determined by the way the two W's decay. If they both decay hadronically, you have the highest branching ratio for the largest background. It's the yellow slice of the pie below. That's called the all jets channel. The lepton plus jets channel is that in which one W decays to leptons and the other to hadrons. That has a moderate background and also moderate branching ratio. And then there are the dileptons where both decays leptonically, and that's the smallest background, but the smallest branching ratio. The original measurements only used electrons and muons. Tau ID was difficult and did not initially attempt the all jets background, all jets channel in which the backgrounds are high. B jets were identified by displaced vertex or by the semi-muonic decays of the top. And neutrinos, of course, were inferred by missing transverse energy. And later on, all the channels were in fact used for studying the properties. Next slide, please. In 1993, both CDF and D0 were seeing individual events that looked extremely interesting. The CDF dilepton event had two quite high transverse energy jets. One of them was B-tagged, had an isolated electron and muon of moderate PT, and a substantial missing energy. The 1993 D0 dilepton event had an electron, a muon, missing transverse energy, all with a transverse momentum above 100 GeV, and two moderate energy jets in a region where the background probability was extremely small. And if that event was hypothesized to be from a top anti-top pair, the mass estimate from the single event was in the range of 145 to 200 GeV. Next slide, please. In 1994, CDF published what they called evidence for top, in which they had two dilepton events, 10 lepton plus jets events, all with at least one B tag, and a background of about 6 events. They fitted the mass of the top in the lepton plus jets. What you do is to take all of the observed objects, sort them with the most probable association to the top or the anti-top, use the missing transverse energy to infer the properties of the neutrino, and then reconstruct the mass of the two tops and plot the events as a function of that fitted mass. And you see on the right what that looked like for the evidence paper. Bump in the distribution around 175 for the expected TD bar signal, the background at a lower mass, and the data clearly favoring some component of the TT bar. The observed cross-section, however, was about 2 times that of the standard model, so there was at least an upward fluctuation. And the p-value was 0.26%, corresponding to 2.8 sigma. At the same time, D0 made its selection based on topological variables, the aplanarity, which is the smallest eigenvalue of the momentum tensor, and HT, which is the sum of the transverse energies of all the jets. And the plot on the left shows how that works for the different categories of events, the multi-jet and W-jet backgrounds at the top, falling dominantly at low A and low HT. The TT bar events in the lower left with a sizable component at large A and large T. And on the right, the signal region and the few data events. There were 7 events, the background of 3.2, probability of the null hypothesis, 7.2%, and the rate was compatible with the standard model top pair production. Next slide, please. So in 1995, early in the year, the tevatron performance had been much improved. A magnet that was misoriented was reset. And by that time, both CDF and D0 had more than 50 inverse picobarns on tape and sensed that this was going to be enough for the top discovery. And so the activities ramped up to fever pitch, trying to finalize all the various analyses. And the two experiments proceeded quite independently. There was essentially no communication between them. There was, however, an agreement with the Fermilab director, John Peoples, that either of the collaborations could start the clock for discovery by submitting a paper to him, and then a 1-week waiting period would start, allowing the other group to complete their work if they could. And this induced a certain amount of sanity in the process, since one didn't have to fear being scooped by the other collaboration. And on February 17th, CDF delivered its paper, D0 followed, and 1 week later, on February 24th, the two experiments submitted their papers simultaneously to Phys.Rev Letters. Next slide, please. So here's one slide on the CDF version of the top quark discovery. Their analysis followed the same strategy that the earlier evidence paper had done, but with an improved B-tagging algorithm. And with 67 inverse picobarns, they had 6 dilepton events, 43 lepton plus jets events, which included 50 B-tag jets in that sample. The estimated background was 22 event tags, actually. The fitted mass peaked, most likely fitted mass was 176 GeV with a spread of 13 GeV. The cross-section now had come back. The fluctuation had vanished by that time and was essentially compatible with the standard model. And the background hypothesis was excluded at 4.8 sigma. And on the plot on the right, you see in the shaded regions the estimated background for the lepton plus jets events as a function of the number of jets. And the points show that for the 3 jets and the 4 jet and more, there is a significant excess in data over the background, and that was the evidence for the signal. And the fitted mass distribution looked rather similar to what we had seen before, a peak at around 175 GeV and a background that was peaking lower. So let's go on to the next slide. Look at the evidence from the D0 top discovery paper. D0 also refined its previous analysis using the topological selection, getting a signal to background estimate, which was about 2.5 times better than it had been the year before. And with 50 inverse picobarns, there were 3 dilepton events, 8 lepton plus jets events with a topological selection, and 6 more in which there was a evidence for a muon from a top from the BDK tagging the B-jet. So the estimated background of those 17 events was 3.8 events. The fitted mass best fit was 199 with a very broad distribution. It was actually sort of 2-humped, and a cross-section which was essentially that predicted by the standard model. Background only hypothesis rejected at 4.8 sigma, 4.6 sigma. On the upper right plot is a indication of what this HT selection does in selecting signal versus background, both for the dilepton and also for the lepton plus jets. On the lower left, we have the mass fitted mass distribution, again showing a clear excess of events at high mass and a smallish background at the lower mass. And on the plot in the lower right, a 2-dimensional plot for the top that decays all to hadrons, to 3 jets, the 3-jet mass as a function of the 2-jet mass, where the top is expected to have a 2-jet mass peaking at the W and a 3-jet at the top. And the data clearly has a component of that, but a small component of the lower mass from the backgrounds. The next slide, please. March 2nd, the discovery was announced with the joint seminar of CDF and D0. This is a picture of the audience during the seminar. Clearly, it's an in-person audience, no social distancing, no masks, no one looking at laptops. We didn't have laptops at that time. And you can't tell, interestingly, whether the speaker is from CDF or D0. Next slide, please. So who gets the credit for this discovery? I think in both collaborations, there was a great sense of accomplishment, but a real understanding that there was a shared responsibility for the discovery. There were 6 or 8 different analyses in each experiment. They used the properties of all of the subdetectors that were in the experiments. set of complex triggers and a lot of software algorithms. So it's absolutely impossible to single out a few people who were responsible. It's intrinsically a team effort. And on to the next slide. But the question is whether it was the top. And so to try to settle that question over the next several years, the cross-section was measured to increasing precision and compared to the standard model, and that the theory also evolved to the point where nowadays it is at next to leading order QCD plus next to leading order electroweak, and the cross-section agrees very well with that what you would expect at the observed top mass. The branching ratios are as expected in the standard model. The charge of the object is measured to be 2/3. The CKM matrix element is consistent with 1, as you would expect for a 3-generation quark sector. The W boson helicity in the top decay to a W agree with the standard V-A standard model. And the top polarization was essentially 0 as expected, and the spin correlations were as expected. So indeed, it looks like it is the standard model top, but it is certainly an odd object because its mass now is 40 times that of the next heaviest quark, the B. Also, it has a very short lifetime, 3 × 10⁻25 seconds, which means that it decays before the QCD hadronization can occur. And so there is no TT bar bound state as there is for all of the other quark anti-quark pairs. Next slide, please. So top now is approaching middle age after 25 years. The Tevatron told us a lot about it, but now the LHC has taken over, and it's interesting to see what new information comes from the measurements at the LHC. Here we see the top pair production plotted as a function of the TT bar mass, and on the left, at the Tevatron, this is the D0 plot, going up to about 1 TeV for the TT bar mass before the rate goes to 0. The red histogram is the prediction of a standard model, which is therefore clearly representing the data very well. On the right, we have on a log plot the same distribution from Atlas, now going out to 3 TeV in the TT bar mass, thanks to the development of boosted the observation and handling of jets that merge together at the LHCs, allowing one to go to very high transverse energies. And there are no TT bar resonances or anomalies that are observed. Everything is as the standard model would have it. Next slide, please. The mass is probably the most important property of the top to understand clearly. And it has been measured in many different channels and many different analyses. The ordinary technique is to reconstruct all of the objects in the TT bar decay into the top and the antitop, and then calculate their invariant mass, either for the most likely configuration or for the average of all of them weighted. Different analyses are different, and to compare that to a set of templates from Monte Carlo, which are constructed for different assumed top masses. And what one sees in the Tevatron on the left and the LHC on the right is very good agreement with those templates and an ability to pinpoint that Monte Carlo mass to high precision, 0.37% at the Tevatron and 0.29% at the LHC. A couple of years ago, I have not seen a recent measurement there. But the problem is that, and these measurements have now become essentially systematics dominated. So going further requires something new rather than statistics. But there's a problem in that the mass that one measures here is whatever it is that is embedded in the Monte Carlo. And what you would like to have is a mass that has a clear theoretical meaning, something like the pole mass or the MS bar mass or whatever. And to do that is more difficult. It can be done, and it has been done at the Tevatron and at the LHC in the plot at the bottom. If you compare the theoretical cross-section and the experimental cross-section, both as a function of the top quark mass, and find where they intersect, then one has a measurement within the standard model context of the pole mass. And at the Tevatron, the best measurement is from D0 with an uncertainty of 3.4 GeV. At the LHC, a very recent measurement from CMS makes a drastic improvement to 0.8 GeV by using not only the cross-section, but two other distributions, and making all three of them compare the data and get good agreement between data and the theoretical. So here the LAC has actually made a very large step forward. Next slide, please. The TT bar production is asymmetric, forward backward at the tavitron, because it is an initial state of antiproton and a periton, and therefore the periton is the top quark tends to go preferentially in the hemisphere containing the exit periton beam, and vice versa for the antitop. And that asymmetry comes about from the interference between leading order and next to leading order diagrams in the QCD production. Early on, those measurements had a rather large discrepancy between experiment and theory. And what's happened over the years, shown in the plot on the left, is the data has come down in the asymmetry. Here it's plotted as a function of the TT bar mass. And the theory has gone up so that the yellow line of the theory now comes rather close to the experimental points, and there's no more large tension between theory and experiment. At the LAC, with the PP initial state, you don't have that forward-backward asymmetry, but you do have an asymmetry in that the top quark is expected to be produced more forward than the antitop. And so you can do a central forward kind of asymmetry, which is quite small, but now at the LAC, it's beginning to be measured. It's less than 1%. And so this is a tough measurement. Next slide, please. Production of a single top has been a very important aspect of top quark studies. It's produced through electroweak diagrams, the exchanges of W's or the involvement of W's in the process. Three main processes exist: the T-channel exchange of a W boson, the S-channel exchange of a W, or the S-channel exchange of a B quark, producing a final state of a top and a W. The top W process is small at the tavitron and was not seen there, but the other two were, the S-channel and the T-channel. At the LHC, the S-channel process is small and has not yet been seen, but the TW and the T-channel have been seen. And if you compare the T-channel, which both accelerators have observed, you find that the cross-section is very much larger, factor 50 or so, than at the tavitron, but that the precision with which that T-channel process is measured is essentially the same at the tavitron and at the LHC. So here again, one has a rather strong systematics dominated character to the measurement. Also, the couplings that had been seen at the tavitron have been measured again at the LHC. The W helicity, which is expected to have no right-handed component, the LHC has improved the tavitron limit by about a factor of 4. The top-bottom W V plus A coupling, which is expected not to exist, the tensor couplings, the LHC has improved over the tavitron by a factor of 2 or so. Next slide, please. And the LAC is adding a lot that is new, that was never done at the tavitron. For example, top pairs or the single top can be produced in association with another object, a Z, a W, a photon, another TT bar pair, or a BB bar pair. And all of those are windows into the possibility of new physics. One has now also observed the top Yukawa coupling at the LHC via the measurement of the process production of top, antitop, and Higgs, with the Higgs decay into BB bar, gamma gamma, or ZZ star. Comparison of that with the indirect Yukawa determination from gluon fusion processes in which you produce a Higgs that decays to 2 photons, and comparing those constrains the possibility of new physics in the loops. Also with the Higgs, we're now getting into the second generation coupling, with very recent observation of the Higgs decay into dimuons, so the evidence for it. Also, as the high luminosity of the LHC comes along, we'll be able to search for new physics. For example, the flavor changing neutral currents in top decays to charm Higgs or into charged lepton non-universality. The plot on the left is the recent determination of the Higgs decay into 2 muons, showing that again, the couplings are falling on this proportionality to mass that is expected in the standard electroweak mechanism. And of course, like it always is the case, yesterday's discovery is tomorrow's calibration, and that's true for the top, where studies at the top have helped us fix the jet energy scale determination and also the BTEG efficiency for studies searching for new physics. Next slide, please. The self-coupling term in the Higgs potential is shown here, the lambda 5/4 term. That lambda runs, as does alpha S and alpha EM and so forth. And as Q squared gets large, lambda decreases and could in principle become negative. And if it becomes negative, then the Mexican hat Higgs potential turns over so that the absolute minimum is no longer at the usual vacuum expectation value location, but there is a secondary maximum that is a minimum that is larger at higher expectation value, or becomes unstable altogether, and the universe becomes unstable or metastable. The current values of the Higgs mass and the top mass indicate that we are probably in this metastable region, in that yellow region between instability and stability. Although the uncertainty is such that we can't really tell whether we are in that metastable region or in a region that is absolutely stable. It's interesting to speculate whether or not there's a clue here that nature has arranged things such that we live on this boundary between stability and instability. Is that significant, or is it a coincidence? Presumably coincidences do happen. For example, if you look up in the night sky at the time of an eclipse, you see that the size of the moon and the size of the sun are the same, but that interesting observation, of course, has no bearing on anything. Let's go to the next slide, please. So what is the character of our expectation for what we will learn when the top becomes more mature still? Well, we'll have the high luminosity LHC, and with a very large statistics, we'll be able to go into kinematic regions where lower systematic uncertainties can be found, and therefore improvements on things like the pole mass can be made to improve. And we'll also get into the range, the region where very rare decays can be probed, and if found, will signal the presence of new physics. Future E plus E minus colliders will go even further. For example, the ILC can scan the energy in E plus E minus going to TT bar pairs, as shown in the right-hand upper plot. And if you do that threshold scan, you have a very precise measurement of the turn-on of the top quark threshold, enabling you to find to measure the mass to a precision of about 50 MeV, which is about 1/16 of the current precision from LHC. In the ILC, the Higgs mass will also be improved by a factor of about 10. So the plot on the left indicates the comparison of what we know now about this metastable region to what we will know in the era of the high precision E plus E minus machines, shown by that dot in the middle, and will clearly resolve this question of what region are we in. It is also true with the improved precision on the top quark mass and also on the W boson mass, that the constraints on non-standard model physics from the comparison of the directly measured Higgs mass and the indirect prediction based on the top and the W will be one of the best indicators of the presence of new physics in the loops of the various diagrams. Okay, next slide, please. And I will conclude. So the biography of the top has thus far gone through infancy, where the top was discovered at CDF and D0 and opened the era of the studies. In its youth at the LHC, we are extending our understanding of the top quark significantly. In its maturity further on, we expect that the studies at the high luminosity LHC and a future E plus E minus collider will bring qualitatively new insights and that these will be important because precision top measurements explore the third generation physics, where we expect that the new physics should be the most visible. And it also highlights the question. The top Yukawa coupling is essentially equal to 1, and you can ask whether this is an anomaly or is it the standard way a quark should behave, and that the up, down, strange, charm, and bottom are the peculiar quarks in the universe. So thank you very much. It's been a pleasure to join you, if only remotely. Next year in Moscow, I would hope to join you in person. Thank you.
Thank you, Paul. Any questions, please? Question in chat. I do not see actually, except thank you very much.
Hello, I have a question.
Yes, please.
Hi, Paul.
Hi.
It's very interesting that now when we talk about the top quark mass, we move from the early days of direct reconstruction of something that would be interpreted as a Monte Carlo mass to now a scan of cross sections for the most precise measurements that relate to the pole mass. Is there something to be learned about the comparison between the two? Maybe something that has to do with running of alpha S or QCD corrections at the top mass scale?
I think I don't know. I think it's difficult to pinpoint what it is that is in the Monte Carlos and how it relates to any theoretically well constructed mass. I suspect you may be right, but I don't think I'm able to articulate how that insight into a running parameter would come about.
It's something that I haven't heard discussed too much, but it might be
I
an
have not
opportunity to turn this challenge around and
Yes.
maybe learn something from it.
Yes, it's an interesting question.
More question, please. Okay. Paul, thank you very much for your very impressive report. And thank you everybody for participation in this session. I hope that we will have a lot of interesting information now to think over. Thank you very much.